Okay, let's continue with a sample problem. An embankment is shown in the figure. Determine the stress increase under the embankment at points A1 and A sub 2. So we are given with an embankment. So this is the embankment. It has a height of 7 meters. So from this point, you have dimensions 14 meters, you have 7 meters and 14 meters. So what would be the stress at point A sub 1 and point A sub 2? So that we can, okay, let's have the stress first, the stress at point A sub 1. So to get the stress at point A sub 1, we're going to have this illustration. So basically, we try to isolate halfway. So to the right, to the left of point A sub 1, to the right of point A sub 1. So basically this one, this Q is equal to 7 times 17.5, which gives us 122.5. Of course, symmetrical, so this is also 122.5 kilonewton per meter squared. So basically for that, we have to get on the left side, we have for the stress increase of point A sub 1, on the left side of the figure, we have B sub 1 is 2.5 meters, and of course our B sub 2 is 14 meters. So if we're going to get B1 over Z, that is 0.5, and B2 over Z is 2.8. So from our figure 10.20, we can get the value for I sub 2, since we have the value of 0.5 and 2.8. So our I sub 2 is approximately 0.445. Since if you're going to observe from here, this is our B1, this is our B sub 2. So our B1 is 2.5 and our B2 is 14. So this is on the left side of A sub 1. Since this is symmetrical, so whatever is the value on the left side of A sub 1 similar to the value for on the right side of A sub 1. So meaning to say that is symmetrical, so on the right side of A sub 1, I sub 2 is also 0.0445. And you simply have to sum up the value for the two. So you multiply that one by our Q. The Q times stress at A sub 1 on the left side, and Q times the stress at A sub 1 on the right side. So we try to simplify that one. So the stress increase at point A sub 1 is 109.03 kilonewton per meter squared. So how about the stress increase at point A? For the stress increase at point A, you consider we have the left side. So this is our point A sub 2. So what will be the stress at A sub 2? So we're going to have three figures here. On the left side of A sub 2, on the middle section, and in the right side of A sub 2. So on the right middle section is this part, then you have the right side of A sub 2 in this portion. So what you're going to do is you simply get the stress on this portion, the stress on this portion, the stress on this portion. Whatever is the value for this, you simply have to add the stress here, and the stress on the middle portion subtracted by the stress on this portion. So you simply have to get our B2 on the left side of A sub 2, our B2 is 5 meters, our B1 is 0, because you have here the left side, B sub 1 is 0, B sub 2 is, basically you have B sub 2 is 5 meters, B sub 1 is 0 from here, from this figure. So B sub 2 is 5, B sub 1 is, B sub 1 is 0, we don't have value for B sub 1. So that would be 0. So let's get to have now your B2 all over Z, that is 1, B1 all over Z is 0. Then, based on this value, our I sub 2 from the figure 10.20, that is 0.24. And we multiply that by our, the value for our Q, which is from this figure, our Q is, this is 2.5 times 17.5, so we get now the value. This is now the height. Basically, that is the height of our So this portion, this one. So basically, you get this as 2.5. You can have ratio and proportion. Ratio and proportion by this portion over this, then this portion all over this. You can get this value. So that is 2.5. So that is 2.5. So you multiply 2.5 times 17.5, you get 43.75. Multiply that one by I sub 2, 0.24 gives us 10.5 kilonewton per meter squared. For the middle section, our B2 is 14, our B1 is 14. So this is our middle section for this one. For this one, this is our B1, our B2 is 14, our B1 is also 14. So we get the ratio here. So B2 all over C, that is 2.8, B1 all over C is 2.8. So using figure 10.20, I sub 2 is 0.495. And multiply that one by 122.5 because the height is 7 of the embankment is 7 times the unit weight of the embankment, which is 17.5, we get 122.5, which is our Q times I sub 2, 60.64, that is now the stress on the middle portion section. On the right side, our B2 is 9, our B1 is 0. So on the right side, this is the right side of A sub 2. You have B2 is 9, B1 is 0. So for that, you get your ratio B2 all over Z, which is 1.8, and B1 all over Z is 0. So we get now our I sub 2, which is 0.335. We multiply that one to our Q, which is 78.75 of this figure, because this one, we get now 4.5 times 17.5, we get 78.5 kilonewton per meter squared. So from that, we can have our we multiply that by 78.75 by I sub 2, we get 26.13 kilonewton per meter squared. Now the total increase of point A sub 2 will be, you simply have to add the stress to the left of this A sub 2, the middle section, you subtract by the stress to the right of A sub 2, and that gives us 44.76 kilonewton per meter squared. So that was the sample for stress due to embankment loading. So we move on now to this vertical stress below the center of a uniformly loaded circular area. So for this one, what will be the stress at point A due to a uniformly loaded circular area? So we're trying to have a point A, the stress at point A, which is directly at the center of the uniformly loaded circular area. So for this one, we have this equation. You have to get the value for our R, capital R, which is the radius, over Z, the distance from the center towards our point A, that we're going to get our stress, and our Q, that is the load acting on a uniformly loaded circular area. So that can get our vertical stress. So we have here the variation for our delta sigma sub Z all over Q with the value of Z all over R. And for the vertical stress at any point below a uniformly loaded area, so what will be the stress at any point below a uniformly loaded area? So the stress that you're going to compute is not directly from the centroid of the uniformly loaded area. So this is what will be the stress here due to this uniformly loaded circular area. So that we can compute that one, we have this equation. So that is the stress at any point due to the uniformly loaded area. The uniformly loaded circular area is equal to this equation. We just have to get our A prime and B sub prime, which is a function of Z all over R and R all over R. So from there, you can get now the stress at any point below a uniformly loaded area. So we have here also a figure for the variation of your delta sigma all over Q with values of r all over r and z all over r. So we have your sample problem. Consider a uniformly loaded flexible circular area on the ground surface as shown in the figure. And this is the figure for our sample problem. We are given with our radius 3 meters and a uniform load of 100 kN per meter squared. Calculate the increase in vertical stress at depths of 1.5 meters, 3 meters, 4.5 meters, 6 meters, and 12 meters below the ground surface for points at r equal to 0 and r is equal to 4.5 meters. So for this one, this is the equation that you're going to use. Delta sigma sub z is equal to q times a sub prime plus b sub prime. So our radius is 3 meters and q is 100 kN per meter squared. So for this one, we are given with our depth, which is 1.53, 4.56, and 12. So we have to get the value of z all over r, so that we can get the value for a prime and b prime. Once you have the value now, based on our table 10.7 and 10.8, you can get the value of a prime and b prime. Once you have the value for a prime and b prime, you can get for our stress, delta sigma sub z. So from there, you substitute the value for a prime and b prime to this equation. You have now our values for stress due to the flexible circular area at a certain depth, 1.53 meters, 4.56, and 12 meters. So these are now the stresses caused by a uniformly loaded flexible circular area. So, of course, we have to identify our r all over r, which is 1.5, so that we can get now our stress at 1.53, 4.56, and 12 meters depth. So you simply have to substitute our equation q times a prime plus b prime. So this is now the value for our stress at z is equal to 1.53, 4.56, and 12 meters.